And now our next spotlight speaker. We are very happy that AGS Councilor Chris Verlinden has been able to join us today from Entanglement. Chris?
So I'm told whenever hosting events before 10 a.m. you're supposed to keep all the topics kind of light and easy, so I'm glad we're talking about next-gen geophysical fluid dynamics and quantum computing. Let's dive right in. My name is Chris Verlinden. I'm the CTO and co-founder of Applied Ocean Sciences, and as of recently, the acting chief scientist of Entanglement Inc. Our two companies are in the final stages of a merger, and I know what you're all thinking. You might be wondering, why would a company in the cutting-edge, super sexy, and incredibly profitable field of oceanographic research want to merge with something as pedestrian as a quantum computing company? And the answer is just to throw them a bone. We figured they needed a favor. We figured, those theoretical mathematicians needed some of that sweet, sweet oceanography money. So, we figured we'd do them a favor, we'd do a merger. It also turns out that some of the earliest and most effective quantum-inspired algorithms and quantum computing ecosystems are actually fundamentally very well suited for the problems that we spent our entire careers working on. If quantum computing is not a topic that you have a lot of comfort with, you should probably just join the club. I really like this little cartoon. I've seen it and I've applied it to a variety of disciplines. And if you plot, I think this has always been true for me, my knowledge of a particular field on the x-axis and the confidence in my viewpoints on the y-axis, when I first learn about a discipline, I get real confident real quick because I just think I know everything, I learn it, and then eventually you start to realize that as you ask more questions, you end up with more questions than you did at the beginning, and you realize you actually don't know that much. And then that's really where you start to get this sort of precipitous fall off to right about here. And then after a few decades, you start to realize, I actually do know a thing or two, and your confidence starts to go up, and then you die. So that's generally how it works for me. And right about here is where I was starting to feel where I was as a mathematician, as a computer scientist, as an information theorist. I was feeling pretty good about 10 years ago. I was like, I'm advanced, I'm not dead yet, and I'm sitting right there where I'm starting to feel pretty decent. And then I found out about quantum computing and started diving deep into it, and this has been my trajectory ever since. And in fact, it doesn't quite do it justice, because this is about where I am today, and it just keeps falling. And I don't know when it's gonna stop. So if quantum computing is a topic that you think you don't understand, like I said, you should join the club. To me, the world is divided into two groups of people. People who don't understand quantum computing and liars. So I'm not a liar. I know a few things and I've used it for a variety of problems that I find very interesting, and I hope you do too. I want to start with a quote from Jason Turner, a visionary leader and the CEO of Entanglement Inc. I'm not just saying that because he's my new boss. I'm saying that because he's my new boss's boss's boss. This is a quote that he often says, and I really like it, so I'm going to steal it. Nations are competing to win the AI race. Winning requires complex math to power trusted AI. Trusted is a key word there, at scale, to make it sustainable. Entanglement humanizes intelligence to win this race, creating global powerhouses and elevating humanity. And you can read these words if you want to, but my simplification on that is what we do is we have some of the smartest, most awesome people I've ever had the privilege of knowing and working with, creating algorithms, new technologies, be it computing hardware, computing infrastructures, or algorithms. And we build up these algorithms and then build up business use cases around it. So far, those business use cases have been detecting anomalies in computer systems in order to do cybersecurity. It's included making a microplastics detector for clean drinking water and maritime security. And I'm going to talk a little bit about each of those things today. So the title of my talk has quantum-enabled GeoAI in it, and I figured it would be irresponsible to talk about that without at least giving a definition a shot. So when I say quantum-enabled, I'm not just talking about quantum computers, and I'll talk a little bit about, what there is beyond quantum computers and also what I mean when I say quantum computers, but I mean quantum computing or quantum-inspired algorithms as an enabling technology to do GeoAI. And when I say GeoAI, I really just mean geo, meaning the questions, the decision-making, the thinking, the data is spatial in nature. And when I say AI, I mean it in the broadest possible sense: artificial intelligence, machine learning, adaptive regression, basically where the data is allowed to alter not only the parameters and the coefficients in your algorithm, but the structure of your decision trees as well. And so that's what I mean when I say quantum-enabled GeoAI. When I talk about quantum-enabled technology, like I said, I'm not just talking about quantum computers. Quantum computers are awesome. We could do a whole session on them and still barely scratch the surface. One thing that's important to know is not all quantum computers are the same. In fact, they're different, more different from each other than a quantum computer is from a classical computer in some cases. So there's the classic superconducting loops and trapped ions, silicon dots, topological, diamond vacancies, all those very, very cool pure quantum processes. There's also sort of these hybrid systems like quantum annealers. D-Wave makes some super cool computers that we use for a lot of our problems. And then there's these photonic computing architectures. And all of those things are based on quantum processes. And if you use a quantum process to perform a calculation or set of calculations, it's a quantum computer. In a class I taught at the Coast Guard Academy when I was a professor there, when we were talking about sort of computer science at the most fundamental level, I used to challenge them to try to create a computer with plumbing. To basically try to use the fluid dynamics of flow through a pipe in order to answer mathematical questions and perform computations with water flowing through pipes, and all of them were able to do it. So the key is if there's a physical phenomenon that does a thing that you can combine in ways, gates, logic gates, et cetera, to perform a calculation, that's a computer. And a quantum computer is just something that does that with a quantum process. By that definition, a regular computer is kind of a quantum computer. But it's not just quantum computers that are quantum-enabled technology. One of the really cool and exciting developments lately has been the algorithms we've developed and started thinking about and the way we think about computation in order to start using quantum computers for their full potential have also led to a bunch of algorithms that can actually be emulated on a classical computer and still provide significant savings and computational efficiency. So those algorithms include quantum unconstrained binary optimization, or QUBO, quantum and simulated annealing, sort of next-gen simulated annealing, taboo search, meta-heuristics, physics and context-informed neural networks with specific types of probabilistic physics. And a lot of those algorithms can be run on a classical computer. So one of the things that turned me into a convert in quantum-enabled technology is it's the one time I ever won a bet with the former deputy at DARPA, Peter Hyman, if you've ever met the guy. I once bet him that he said there was no problem you can solve today that you can't, with a quantum computer that you can't solve better with a classical computer. And that was like in 2017 or 2018 or so. And I said, I disagree, because I was combative. No other reason. I had no idea what problem it was going to be. And he said, prove it. So it took me about a year, but I ended up setting an acoustic tomography problem, where you use the travel time of sound to measure the temperature in the ocean. And that underdetermined acoustic tomography problem that involved matrix inversions and a bunch of stuff that was just perfectly suited for various families of quantum computing. Took my laptop, it was in M1 Mac, very fast, about 2 days to solve. It took the algorithm that we ran on a $15 million D-Wave quantum annealer less than a second. If you don't have $15 million, something that's been very exciting to me lately is just recently I implemented that exact same tomography problem on that exact same Mac. I should probably replace it. But on that exact same computer, using a quadratic unconstrained binary optimization in place of my classic simulated annealer for optimization, and it ran in 10 to 40 seconds, depending on certain parameters. So some of these algorithms that we've developed for quantum computers can have significant computational advantages for classic problems, even without a $15 million quantum computer. So you might ask yourself, why do we care? I care because I'm an oceanographer, a climate scientist, and in oceanography and climate science, environmental science, remote sensing, maritime security, all of the things that I spend my time doing, there are a large number of problems that are fundamentally well-suited for quantum computing and quantum-inspired algorithms. My simplistic understanding of those problem sets come down to basically two types of problems. Problems that are well-suited for quantum computing can include problems that are fundamentally probabilistic, where the answer that you want is not a yes or no, but you want a probability. Good examples of those problems are like molecular design. If you're modeling a quantum process and the quantum world is fundamentally probabilistic down to the truth of it, then using a quantum computer to model a quantum process with similar probabilities is very well suited. Similarly, if there's a problem where you don't actually care if you get the right answer, that also is a good problem for quantum computers. And you might say, well, why would I ever not care that I get the right answer? Well, the whole reason that we're worried about quantum computers for cryptography purposes is that most cryptography standards are based on prime factorization. Prime factorization is a mathematically intractable inverse problem with an easily verifiable forward problem. What I mean by that is if you run a prime factorization on a big, let's say 200-digit number, and you get an answer, and it's right, wrong, you have no way of verifying it, multiply the numbers together. If they don't get you back to that original number, it's wrong, try again. And if you can try a few thousand times in a few seconds, suddenly you can solve a problem that used to take a computer the size of the universe, the age of the universe to solve in a few seconds. And that's why quantum computers can be very well suited for intractable inverse problems that have easily verifiable forward problems. And an entire family of problems that's based on that is anything that has a underdetermined or not full rank matrix inversion, which over the course of my career I realized is literally the only thing I do. Every single problem I solve, for some reason, seems to have matrix inversions in it. And that's optimized searches, search and rescue patterns, where to put your robots if you try to find a submarine or a ship, the tomography problem of trying to fit functions to an observable data set. Even the algorithms that drive some of the sensors that we've been developing end up being matrix inversions, optimized searches, and ensemble-based approaches where, again, the answer is fundamentally probabilistic. This is why I care. So, if you know what we're looking at right here, you can shout it out anytime. This is a super cool visual made by NASA's Scientific Visualization Studio. And what we're seeing is the Pacific Ocean and the water temperature in 4 dimensions. And there is red and blue. Blue, unsurprisingly, is cold. Red is warm. And there's an effect in the ocean called El Nino, or a Nino Southern Oscillation. And what that is cold water, typically, is on the eastern side of the Pacific, and warm water pools up on the western side of the Pacific. And under El Nino conditions, that warm water basically jets across, and you end up getting much warmer than usual water off the west coast of the Americas. Look at that big red blob. And when El Nino happens, you end up getting huge consequences. You can have crop failure, you can have fisheries collapse, you can have socioeconomic instability, there's famine, there's drought, there's fires, people die. The implications of El Nino are absolutely massive, and yet it might surprise you that we actually can't predict it. We're very, very bad at predicting El Nino, and part of it is because all of the reasons that Tosca talked about. The ocean's hard to observe, it's hard to get enough data there. In the talk we just saw, we said we have a lot of data. There actually aren't that many of those dots in the ocean, so more data would certainly help. But something that's interesting to me and that makes me motivated to keep working on these problems is that we actually get all of those physics. It's one equation, Navier-Stokes. If we had enough observations and threw enough compute power at it, we should absolutely be able to solve that problem and predict El Nino. I can't, but someone should be able to. And that's why it's so exciting to be working on this type of work right now. Because for the first time, I think, we have computers that are powerful enough, algorithms that are sophisticated enough sensors in the ocean that we can actually start solving these types of problems that have trillion-dollar and life-altering implications. And so if anybody asks, why do you become an oceanographer? It's because there are problems like this that are still left to be solved, and that's super exciting for me. So the applications I'm going to be talking about today are not El Nino, because I haven't solved it. But the things that we are using quantum-enabled GeoAI for today is maritime domain awareness, environmental decision-making, and the very broad category of novel physics. So let's talk really briefly about maritime domain awareness. It's a term used in the intelligence community, defense community, homeland security, et cetera. Basically, that says you want to know every ship everywhere all at once because you want to know what's happening in the ocean. And that involves knowing the environmental conditions, the weather and sea state, the variables that Tosca talked about that SOFAR is working on. You want to know where the ships are, the aircraft. You want to be able to detect anomalies. And the primary way this is done, and a lot of really cool organizations are doing really good work in this space, is you have a whole bunch of space-based sensors. You have commercial and publicly available data sets, environmental data sets, like those generated at SOFAR, like the ones generated by the National Weather Service. You take all of the positions of vessels that you know who are broadcasting their position, AIS, VMS, et cetera, and then you fill in the gaps with your own autonomous vehicles, with your own sensors. And that's where it can get a little bit hairy. Because if you want to know what you can see, what you can't see, what you can detect, what you can't detect, you first need to know the environment everywhere. This is actually not a model of wind. This is a model of wind noise under the surface of the ocean. Wind stirs up the surface, makes waves, and it makes it loud underwater. If you're under a hurricane and you want to find a submarine, you have a 0% chance of finding that submarine because the submarine's quiet and the hurricane is loud. So if you want to know where to put your sensors, you need to know what the sound is everywhere. And this particular model was run by my business partner, Kevin Heaney, and slash boss, and it's really good. But the point is, even this isn't quite enough because unfortunately, the wind is not the only thing making noise in the ocean. You also have ships. In fact, you have about 700,000 ships, depending on where you draw the line between boat and ship. And so you need to be able to model all of those all the time. And what Kevin and I have spent most of our careers doing is coming up with the most efficient possible models we can think of in order to do this. And now what we're working on, with SOFAR and all of their buoys as well, is starting to assimilate observations into these models. Those data assimilation problems are perfectly suited for quantum-inspired algorithms and quantum computing, because essentially it's an infinite guess and check problem. You assimilate your observations, you wiggle your surfaces and your parameters until you get the best possible match. And I just trivialized Kevin's 50-year career doing it, but if you can wiggle those surfaces more, faster, better, that's a very good thing. And so searches like Cubo, like Taboo Search, end up becoming a very powerful tool for data assimilation. So once you know the environment everywhere, let's say you want to deploy a bunch of autonomous vehicles, surface, underwater vehicles, whatever it is, they carry sensors. We've been working on a program we call Maritime Information Superiority Tools, which allow us to deploy those assets in the most optimal way in order to achieve the objective that you have. It might be to detect a certain type of, maybe it's a semi-submersible smuggling vessel. Maybe it's to just actually measure the environment and constrain it to within a certain output variance. And so what it allows you to do is optimize your laydown of a variety of assets like the CSAT autonomous vehicle, the SOFAR spotter buoys, Sea Explorer, profiling floats, and you can lay them down in a way that is optimal in order to get coverage. So this is just a quick case study we did where we did an optimal laydown of buoys that measure acoustically and with radio direction finders, RF anomaly detection off the port of Bahrain. And if you had tried to lay these down without thinking about all the environmental parameters in the models, you probably would have thought you needed about 20 buoys to do this, and we were able to do it with, it looks like 7. And so using the optimization schema, we were able to do a job better for significantly less resources, in fact, less than half in this particular case. Maritime domain awareness is one application we work on, but another thing we work on is something you guys got a bit of a preview for yesterday in my colleague and sister-in-law's talk at the end of the day yesterday, where she was talking about Quantum Almanac. And so Quantum Almanac is basically a set of environmental prediction tools that are based on those same technologies. And the way she described it is better than how I could describe it. But the Farmer's Almanac in days of old is basically just people who paid a lot of attention to a thing that mattered to them. It's really, really hard to predict if it's going to be raining at 2 o'clock on a Tuesday a month and a half from now. In fact, it's impossible currently. Maybe all that AI stuff that we just heard about can help with that. But it's currently impossible. But if you don't care about that, let's say you're a farmer and let's say your crop yield is entirely based on the pollinator activity in 2 weeks out of the year, which is the case, by the way, for almond crops, it's actually not that hard to predict a month and a half from now how many days in that 2-week period are going to have a frost day, how many days are going to have an average wind over a certain amount. And bees apparently don't like frost or wind. I'm not a biologist. But if you can predict those types of things, which are much easier to predict in a probabilistic way using ensemble forecasts, suddenly you can map those parameters to things that matter to that community. So we use a 3-dimensional risk matrix where you have severity of a certain thing happening on one axis, likelihood on another axis, and then essentially your ability to do anything about it on a third axis. And when you put it together, it becomes a decision engine for insert your community here. It could be farmers, it could be water planners, it could be anybody. So the product that's based on that Katie talked about yesterday is Quantum Almanac. And I had to use AI somewhere in the talk, so I had it draw this picture for me. And I was super impressed with it until like 5 other pictures over the course of the last 2 days looked exactly like it. So I'm starting to wonder about the creativity of some of these AI engines. Novel physics, we could go on and on about that. I would love to, but a sort of counterintuitive one that I just find to be awesome application of some of these next-gen computing technologies is actually in a microplastic sensor we've been developing that can detect tiny amounts of plastics in drinking water. And the approach uses ultrasound, and we map the ultrasonic transmission levels to the concentration and composition of plastics in the water. Turns out that's an insanely computationally intensive operation, without using some sort of globally optimized search. Spoiler, it's Cubo. I used to be accused occasionally of being a one-trick pony where I'd use simulated annealing for everything. I'm now a two-trick pony. Now I use simulated annealing in Cubo for just about everything, and it turns out that we can actually use those types of optimizations in order to design the actual algorithms that run this sensor. We can use, for, again, novel physics, we can start to use these sort of optimized search for acoustic modeling. This shows acoustic propagation through the ocean. It's very nonlinear and it's very dynamic. We can use it for data assimilation, like I said before. If we were to take SOFAR spotter buoys, for example, anywhere here in this ocean, and basically rubber sheet all the parameters that go into our acoustic model based on those observations, again with an optimized search, we can end up generating noise maps of the entire planet for a fraction of the computational cost of what this would have taken before with much greater precision. So what comes next? You name it. Now that I'm a two-trick pony, there's a number of problems that I want to work on. One of the ones I'm really going to highlight here is search optimization, because I think that's a very cool problem set. We want to use the quantum computers and quantum-inspired algorithms to optimize searches for everything from submarines to people in the water. We want to generate search and rescue algorithms using these types of programs. And I think search theory is a prime place for disruption using quantum-enabled GeoAI. So that's what I want to work on next.